Wow, Emma, class was so interesting today. Wasn't it?
Yes, Laura, it really was. Let's tell everyone what we learned today. A Markov chain is a simple stochastic process with discrete time and state space. It can be illustrated as a transition diagram or a transition matrix. In a transition graph, the circles represent each state, and the arrows represent the transitions in and out of each state along with the associated probability. The transition matrix determines the probabilities of various paths. The entry ij is the probability of moving to state j from state I. The sum of each row in the matrix is 1.
Markov chains are so named because they possess the Markov property. The Markov property implies that probabilities of future events depend on the present but not the past. That is, the probability of future events for the process are completely determined by knowing the current state of the process. These probabilities do not depend on how the process arrived at the current state, or how long it has been in the current state. Consider the healthy sick-dead model, where a person is currently in the sick state. The Markov property implies that either recovery or death does not depend on any further information such as how long the life has been sick up until time t, or how many periods of sickness the life has experienced up to time t.
This is correct, Laura. However, in reality, the probability of recovery or death will very much depend on the length of the illness, and on the number of periods of illness experienced by the life. For example, if the current sickness has already lasted for 6 months, it is likely to be a serious illness, and recovery in the next week is possible, but not likely. On the other hand, if the sickness has lasted only 2 days so far, recovery within a week could be very likely. All models have limitations which must be understood, as no model is a perfect representation of reality.
Are there any true examples of the Markov property in Markov chains, Emma?
A true example of a Markov chain is a game of snakes and ladders. In this dice game, the only thing which affects the probability of a certain event is the current state of the board. The next state of the board depends only on the current state, and the next roll of the dice. That is, given your current state on the board is square 94, the probability of scoring a 6 and winning the game is the same, regardless of how you reach the 94th square. You may have climbed 3 ladders or fell down 2 snakes. This memoryless characteristic is the Markov property.
Now we have discussed the Markov property, let's give a real-life example of a Markov chain. The no-claims discount policy used for auto insurance is a simple example of a Markov chain. Assume discount levels of 0%, 20% and 40%. This is a 3-state Markov chain. The policyholder can move from 0%, state 1, to 20%, state 2, in what is known as a transition of states.
Markov chains can be time homogeneous or time inhomogeneous. The time homogeneous case is when transition probabilities do not change over time, and only depend on time differences. For time inhomogeneous models, the transition probabilities do change over time. Now they depend on the absolute value of time as well as time differences. Transition probabilities are calculated using Chapman-Kolmogorov equations.
Thanks for listening.
Goodbye everyone.